Jonty said that too. I think you'll find that last lap's a fractal around here. Can I just draw everyone's attention to yet another meeting? This one's in October, courtesy of the Royal Statistical Society, so please make a note of that in your diary. And Chris Farrow tells me that there will be more speakers as the meeting develops. So this afternoon we continue our theme of the day, which is stochastic models and stochastic parameterizations. Our next speaker is Judith Berner from NCAR, and you can see that Judith's going to be talking about representing model uncertainty in a number of different ways. So over to you.
Oh, the pleasure of Friday afternoon talks. I had a media training not so long ago, and I was told I have about 10 minutes of attention in the beginning of a talk, after which everybody kind of wanders off. I think on a Friday afternoon it's about 5. So these are my key points. I'm trying to make the case that there is model error in weather and climate models, and that this model error in part arises from the need to parameterize subgrid scale processes. And in the kind of prediction context, this model error tends to lead to overconfident uncertainty estimates and possibly to model bias. And so I'm trying to make the case that there's a need for model error representations. And there's by now a number of methods that people use in the atmospheric sciences. And I will be talking about stochastic parameterizations, and in particular I'd like to put forward the idea that a hierarchy of simulations can be very, very helpful, where the statistical output from the high resolution is coarse-grained and then used to inform a coarser model and the parameterizations of that. And I think that stochastic kinetic energy backscatter is a very nice method to use such a hierarchical strategy. And so we heard by Martin Steinheimer about how well it performs in the medium range predictive context, and we heard by Glenn some of its shortcomings or some of the kind of justification that is needed for it. But I think it is a very nice example for such a hierarchy. Finally, I will be also talking about another way of representing model error, namely by using multiphysics ensembles, and I'm trying to compare a bit the stochastic parameterizations with multiphysics ensembles. So here's just a kind of a plot, this hierarchical parameterization or domino parameterization strategy. So basically the idea is that in these cases where we cannot do these, the influence of the subgrid scale onto the resolved scale analytically, for example, as Christian has done with his stochastic mode reduction, we can always maybe run a high resolution model, learn from its statistics, and then inform a stochastic parameterization on the coarser scale with it. So the stochastic kinetic energy backscatter provides such a framework. But there are others. For example, the cloud resolve and convective parameterization or super parameterization is an alternative, which is something that's used in the atmospheric sciences, where you use a 3-dimensional model, kind of climate model, and then in each of the climate grid boxes you run actually a 2-dimensional cloud model. That would be another example for such a hierarchical parameterization. So here is the multiple scales of motion. Again, Christian showed a really nice plot. There are the different physical processes, and then what's missing here is that the time scale separation or typical temporal scale should be on another axis. And here are the types of models that we're running. So on the large scales, climate models; on the smaller scales, numerical weather prediction; smaller scales, even cloud system resolving parameterization, and large AD simulations. And obviously everything to the left of these cutoff lines, subgrid scales, they need to be represented in some form. This is a diagram by Stoll. It's a fairly old diagram, and well, back then the idea was, well, you have some sort of large scale, you have small scales, you have a spectral gap, and therefore we can come up with bulk parameterizations, and we do only need to represent the mean state of the small scales rather than their fluctuations. But certainly this is the Nystrom and gauge that Tim showed. Here is wavelengths of atmospheric motion, spectral density. This is some sort of observed data, and we don't see such a clear spectral gap. This is a paper by Tim and co-authors in the climate context, but basically I kind of liked here this picture of these interlinking systems. I just changed the labels here, right? So the climate model, NWP cloud resolving, but obviously it's a multi-scale problem, and we need to resolve the interactions between the different scales. And again, the goal is to basically have here your cutoff line and somehow represent these unresolved scales for the NWB and climate model. I actually would make the point that there is a spectral gap, but the x's here were wrong. Here. So there's the mathematicians, and they have their stringent models and their beautiful solutions, and there's people like me. And obviously there's a workshop like this where we're trying to close this gap. There's another point I'd like to make, and this is that this whole notion of that you need a gap in the spectrum is actually not necessary for coming up with perfect stochastic parameterizations. So this is a bit busy, but basically if you just look here at the red line, this model here. So this is a typical slow, fast timescale model, and we've seen examples of that. And I guess Michelle's talk introduced it, was the first one. And here I have some sort of characteristic damping with a slow decorrelation. And here I have some sort of fast process that here is represented just as a autoregressive process of first order, where I envision that this damping is a lot faster. And if you look at this system here, this is the autocorrelation function here in red. And then we go to Richard Kleeman's talk and we find the spectrum. We can do this analytically, and this is the spectrum. And so I just wanted to show this as an example where by definition that we don't have a gap in the spectrum. However, we can come up with a perfect stochastic process for the small scales. Indeed, this is just a stochastic process in itself. So I think the lack of a gap in the spectrum does not mean that we cannot parameterize these scales. I think that stochastic parameterization in principle have a very good chance at parameterizing subgrid scale processes in the absence of a spectral gap. Here is the kinetic energy spectra, and this is in an older version of the ECMWF model. This is here, the black line is the model. This is the rotational part, and sorry, this is the divergent part. And so here in gray is the analysis. So this is our best estimate of the atmospheric state, but it is a model observation product. And so here's this discrepancy in kinetic energy at the high scales. And so the other aspect is that here is a -3 slope for the synoptic scales that then arguably becomes a -5/3 rate as in the observations. But neither the model nor the analysis can actually capture that. And there's some interesting work that's been done originally by Lorenz 96, but there have been a number of papers, including Joe's paper, that look at predictability in that context of the kinetic energy slope. And so there is a scenario where you have limited versus unlimited predictability too. So to get these slopes right might be important especially for mesoscale prediction. Finally, here is another schematic of the potential of stochastic parameterizations. We have here the potential well with weak and strong noise, and here the associated PDF. And here we can see that this potential here, in the absence of noise or for small noise, has some sort of unimodal PDF with a certain mean. And that if we introduce strong noise, we might be able to reach here this second regime. And this will change certainly the variance of this PDF, but also the mean of the PDF. And so the point I'm trying to make here is that a stochastic parameterization can change the mean and the variance of the PDF. So it will impact the variability of the model, things like the spread or the internal variability, but it also has a chance of impacting the systematic bias or the systematic error of these models. And indeed, it has been proposed, for example, by Tim, that sometimes these biases are very, very persistent across models, across resolutions. And so maybe the reason is that all of the models do not incorporate certain subgrid scale processes, and this is why those biases are so robust. Here's my outline. I'm going to talk about parameterizations in numerical weather prediction and climate models. I'll then skip talking about the stochastic kinetic energy backscatter scheme derivation because Martin, thankfully, has already talked about this. And I'll show a few results on the different scales. And I really have an impact. I'm trying to emphasize here that this scheme, these backscatter schemes, they help on the mesoscale, on the medium range scale, and on the climatic scale. Mesoscale is more for short range weather prediction, a few days, a continent, or maybe a country. Medium range is more global, 1 to 2 weeks, and then climatic, everything more than a month. And I'd like to acknowledge my collaborators. Okay, so I showed this plot. This is 2 years old, and I did it when I was at ECMWF, and it was kind of interesting. It was like this is Great Britain here, right? And there was these are predictions, and there was like a probability of rain of 100%, and sure enough, it rained. But these are this kind of so in addition to model uncertainty in the prediction context, we have initial perturbation uncertainty. And so what operational weather centers do is not run one, but a whole ensemble of forecasts. And we heard about ensembles in this workshop. And so the idea is to represent the initial uncertainty by an ensemble of states and to make it flow dependent. That is, that predictable states should have a small ensemble spread and unpredictable states should have a large ensemble spread. And so one can show that on average the ensemble spread should grow like the error of the system. This is what we hope. We hope to predict uncertainty due to initial conditions. And in other words, that means that the true atmospheric state should be indistinguishable from the ensemble system. So basically, we have here this ensemble of a forecast in some sort of phase space. Here's the ensemble mean, and here's the analysis, which is our best estimate of the truth. And on average, we should not be able to say a priori which of those trajectory the ensemble is. It should be just like any ensemble member. However, if you do this at numerical prediction centers, these are 3 big centers here, and you look at the growth of root mean squared error here in solid lines and of spread here in dashed lines from 3 operational centers, you notice that the systems are underdispersive. So that means that the spread grows at a much slower rate than the error. And what actually is done to counteract that is, this is here for 10-day forecasts, RMS error. One inflates the initial perturbations to larger values than we know to somehow have enough spread at the extended range. So the ensemble is underdispersive. That means there's not enough spread. And this leads to overconfident ensemble forecasts because we do think that we know what the atmosphere will do, but on average, the verification, the true atmosphere is outside of that predicted cloud of points. And so certainly this is a form of model error, because forecast error is initial condition error and model error and also boundary error. So manifestations of model error. I think I've shown that on the medium range it's typical that ensemble systems are underdispersive, which leads to overconfidence. And one has to ask if that means that extreme weather events, which are obviously very important for societal needs, are underpredicted. And then on seasonal to climatic scales, we have systematic biases. We have not enough internal variability, which might be important for estimations of climate sensitivity, which means how the climate changes in reaction to certain CO2 forcing or other external forcings. And then certainly we can look at the representation of certain physical processes in climate models and weather models and see how well, for example, do they capture the frequency blocking or tropical variability, organized convection, things like this. And they are very good, but they do have some shortcomings. So talking about representing model error in ensemble system, what has been done? Well, as soon as you have not a single model, but you run an ensemble system, there's a number of things you can do. One is the multi-parameterization approach, where each ensemble member uses a different set of parameterizations. So typically we have parameterizations for cumulus, convection, planetary boundary layer, microphysics, short and long wave radiation, land use, and land surface. So what we can do is use just in each ensemble member a different set of those. Then there's the multi-parameter approach, where we use a single set, but we vary the parameters. And there has been some work done on this, and obviously there is an argument. At least in simple system, you can then estimate those parameters, for example, using data assimilation. And then finally, there's stochastic parameterization, where each ensemble member is perturbed by a stochastic forcing term that represents the statistical fluctuations in the subgrid scale fluxes, or as well as altogether unrepresented interactions between the resolved and unresolved scales. So the second one would be an example where what the stochastic kinetic energy backscatter tries to do. It tries to represent those fluxes from the subgrid scale that scatter upscale and we don't have in the models. And stochastic diabatic tendencies that now have a new name at ECMWF, the SPPT that Martin was talking about. I think it's another form of model error. This is more due to the fact that there might be uncertainty in the value, and we're trying to sampling from the PDF of the possible subgrid scale states. And if I learned something at this workshop, I think the statisticians would call this here structural uncertainty, and this would be parametric uncertainty, and this would be again structural uncertainty. Although this could also mean maybe parametric ones. A bit of history. There have been a number of attempts at remedying a model error in NWP, and here's some work that basically uses the conventional parameterizations. So the stochastic parameterizations, multi-parameterization, multi-parameter, and multi-models. And then outside of the conventional parameterizations, more along this line of a hierarchy of models, is the cloud resolving convective parameterization or super parameterization. And then the non-local parameterization. So Tim has written a number of papers and has long been postulated, A, that we need these model error representations, and then B, that maybe they should be non-local, which means there should be correlations, spatial correlations, which is something that the classical bulk parameterizations don't have, at least not implicitly. They are fully dependent on the large-scale state, and as much as that is correlated, they are, but not per se. And then finally, the stochastic kinetic energy backscatter. So when I started to work on this, I never would thought that a few years later I could already put down like a history of the backscatter schemes as being used in numerical weather prediction. So up here in the top, I mean, originally this was developed in the context of large eddy simulations. On my scales, that was a much smaller scale problem where we need a lot less parameterizations, but it's also shorter time scales. Then it has been applied by Fredriksen and co-authors to simplified models. And then Glenn and Tim had the idea that they really need an alternative stochastic parameterization in NWP, and Glenn proposed in the seminal 2005 paper to adapt these backscatter schemes to the numerical weather prediction context. And so the big difference is that you have to come up with an estimation of the dissipation rate in the numerical weather prediction system. And so only 5 years later, many operational centers have implemented a form of this. So obviously there are the efforts at ECMWF that right now are being led by Martin and Glenn. The Met Office has incorporated flavors of this scheme. The Canadian Ensemble System has incorporated flavors of this scheme. And that was mentioned before, they used to have multi-models, and they are moving more to stochastic parameterizations. And then finally, they're implemented in the mesoscale ensemble system that's being developed at NCAR. Now, these are not completely independent implementations. There are the same people behind these things. But I think they have been chosen to be very successful. Many people want to use them, and the reason is, among others, that they don't know what else to use. But the fact is that if you have a scheme like this in there, the predictive skill of your model increases. So there is a lot of merit in doing so. Here I normally talk about the backscatter scheme and its impact on the mesoscale, but this was Martin's talk. But I would still like to stress the point that I really think the beauty of this scheme is that we can run models on a higher scale, in this case cloud resolving models, and coarse grain them and look at the difference. And this is what Glenn and Tim have been doing. There's a paper by Glenn and Tim 2007 that emphasizes these things. And those parameters then inform the parameters of the backscatter scheme. So here's this forcing, stream function forcing pattern that arises by looking at coarse-grained high resolution and low resolution model. And so here's the kinetic energy slope, and this is what we can put in. So it's purely empirical, as Frank would say, but not ad hoc, it's estimated. I'm going to show some results now. So here's the medium range that was already shown by Martin. And I'm going to now show you a bit about the impact on systematic model error. And then I'm going to branch out to the multi-physics alternatives. So I'm looking at model bias. And so these are atmosphere-only runs with observed seaface temperatures. We're having 40 start dates, 5-month integrations. We just look at the winter. One set is with stochastic backscatter, one without. And the models are compared to the error 40 reanalysis, which is our best estimate of the truth. This is work that was done while I was at ECMWF, so it's a few years old. And this was maybe in Tim's talk. So here's the error of Z500 in between the scheme without the backscatter scheme and the observations. And you can see there these dipoles where the model is systematically wrong. And so here on the right side is the same with the stochastic backscatter scheme, and so the error has become smaller. It's still a similar structure, but there's a potential of these schemes to reduce the systematic model error. And interestingly, this was Tim's point, you also reduce this error if you increase resolution. So the fact that the backscatter scheme reduces the error might not mean that it's really the subkit scale that's responsible to it, but it goes fully along the idea that we want to replace high resolution models with low resolution parameterized, stochastically perturbed model runs, and that would allow us to increase the ensemble size. We had a talk about the constraints on ensemble size and high resolution. Here is to look at a process. This is blocking. This is something Tim Palmer has looked at a lot in the different models. Excuse me. And again, here in black is the observations. In blue is an older version of the model, and here in red, the model with stochastic backscatter. And so although we're putting in perturbations, it seems that we're getting more blocked patterns, which might be actually counterintuitive at first. It's not that we just put in energy and everything has increased variability. In this case, it increases the ability of the system to have certain blocked patterns. These are certain large-scale flow patterns where the atmosphere does not have locally the same variance as before, but you have certain large-scale patterns that are locked in place for a while. This is another interesting result. This is, somebody asked earlier today about tropical convection. These are so-called wave number frequency plot, also called Wheeler-Kilades plots. And this tells you about the propagation in the tropics of convectively coupled waves. The ones here on the west propagate westward, and those propagate eastward. And so again, in an older version of the model, there was, so this is observations, and this was the model. And so here you had too much westward propagating modes, and not enough eastward propagating. And this is a plot when the scheme was incorporated. So interestingly enough, it reduces the westward propagating modes while arguably increasing eastward propagating modes. Oops, I'm trying to. So this improvement in convectively coupled waves again can also be obtained by changing the deterministic parameterizations. So since then there have been developments that improve this picture greatly that have nothing to do with stochastic physics. However, again, it is shown that something counterintuitive happens. We're perturbing the system, but the effect is that it dams those westward propagating scales. So it's not a trivial thing. Finally, I'm going to talk about mesoscale models and comparison to a multi-physics scheme. This is work I've done at NCAR. We developed their mesoscale ensemble system based on the weather and research forecasting model. So this is a scheme that is aimed at smaller spatial scales and shorter range forecasts than what is developed at ECMWF. And I'm going to show 3 ensembles, one control ensemble where each member has the same physical parameterizations, one which has the control physics and a backscatter scheme, and thirdly, one where each ensemble member has different physical parameterizations. I'm looking at 30 cases between November and February 2008, 2009. It's a relative coarse resolution, 40 kilometers and 40 vertical levels. It's being run over the continuous United States, over North America, and it started from GFS initial conditions for the people interested. This is just here kind of an overview. We have here 10 members. Here are the different physical parameterizations, land surface, microphysics, boundary layer, cumulus long and short wave. And we have here a mix of different parameterizations for each of them. This is a point. So obviously, if you would combine all possible parameterizations with all, you would get a very large number. But then you put them in the model and half of them blows up. So the choice of those is somewhat empirical in that everything that blows up is not used. And then of those that do work, I think that the best 10% were being used. So while it's not optimized in some sort of Bayesian network, this is not a bad multi-model. It's one where already the best combinations are being used. Here's to demonstrate some of these forecasts. This is now not over the continent, the United States. This is actually over Korea. And so you have here these tropical cyclones, typhoons. And so here's the analysis, a best estimate of what happened. This is a control physics ensemble. Here is the mean and the spread. So the variance of the ensemble members around the mean. And here are just the 10 members for this typhoon. I forgot its name. And this is the 6-year forecast. And what you can see is here was a very strong cyclone, tropical storm, and interestingly, all these members tried to put one in here, so this is very good. But they also tried to put here a second one in, and it's not quite clear if they maybe don't get the location right. And that's why they're trying to do this. They might be pulled by the data assimilation scheme. And this is with the backscatter scheme. So you see in principle the same thing, but for example here, this forecast here has a single very strong cyclone, and it turns out to be the best prediction for this typhoon. So none of the control ensemble members are as good. This is just an example how these things look if you look at actual predictions of a particular event. Here's some statistics around it, and again, Martin showed it. So this is the spread error relationship. This is a bit a different form. Here is the spread, and so the spread are those lines, and this is the error as function of pressure. So I'm here now in the vertical, and I'm only showing it for 2 times. This is the 12-hour forecast and the 60-hour forecast. This is for you. This is horizontal wind, zonal wind, and this is temperature. And so what you can see is here's the different ensemble systems. So I have the control system, the backscatter, the multi-physics scheme, and finally a scheme where I combine all these multiple physics and have on top a backscatter scheme. I should have said this before. So I have a 4th run that's a multi-physics scheme combined with a backscatter scheme. This is here in magenta. And so first of all, what we see is the system is very much underdispersive. The spread is a lot smaller than the observations, than the, root mean squared error. The other thing I should say is that this is verified against observations. So for the atmospheric scientists among you, there's a big difference. There can be a big difference if you verify against analysis or observations. And this is done against observations just to do something different. And we have to take observation error into account, which will somehow remedy this underdispersion. However, if you include observational error, you still have an underdispersive system. And if you're interested in that, I'm happy to show you the plots, or you can have a copy of the manuscript we submitted. And so you have this underdispersion, and you can also see how the different schemes, how much spread they generate. So interestingly here in temperature, for example, the schemes that have the multi-physics have a lot of spread here in the boundary layer in the lower troposphere. However, the backscatter scheme has much more spread than the control, but not as much. Whereas here in zonal wind, the backscatter scheme, the multi-physics improves greatly over the control physics. The stochastic scheme is better, and the combination is the best in terms of maximizing spread. And qualitatively, we see the same at 60-hour forecasts. Here are some of these skill scores, and earlier this week somebody asked about how those are defined. So we define an event. The event in this case is something like the zonal wind is smaller than minus one standard deviation at each location. So it's some sort of event we define, and then we look how often does this event occur in our ensemble system, how often is it forecast on average, and how often does it actually really occur. So this is the idea about these verification metrics. There's a whole suite of them, and I'm just showing one here. But in the operational centers, routinely one looks at a whole range of these verification methods, and some will be sensitive to the spread and some to the error, and most of them to a combination of the two. And so these differences are really small. I should say this is Breyer's score, and the Breyer score is defined so that the smallest number is the best. So this on the x-axis is the Breyer score. Here is and the vertical is again the height in terms of pressure. And so the smaller the score, the better is the system. The other thing is I'm showing here 4 events. These are very events where U is smaller than minus 1 standard deviation. Those are events for very strong wind where it's more than plus 1 standard deviation. Excuse me, these are westerly winds and these are easterly winds. And those are more towards the mode of the distribution. Those are events where the wind is between minus 1 standard deviation and 0 and plus. And I did do this because I wanted to see if the schemes have a different effect on high anomalous events, on kind of extreme events in this definition, as opposed to more common winds. But in short, we see that both the backscatter scheme and the multiphysics schemes have smaller scores than the control physics, but that if we combine the two, which is here the magenta line, especially here in the boundary layer, in the lowest layers of the atmosphere, the skill is best. And the symbols here have to do with statistical significance, so I can show that this is statistically significant, this result. So here I'm just summarizing, comparing here the Breyer scores between the control, basically the control ensemble system, the system with multiple physics packages. So here's always the control, here's physics, here's the stochastic backscatter, and here is the combination of the two. So, so this is a pairwise comparison. And here's the diagonal, and so whenever so these scores are now for all vertical levels and for 3 different variables: zonal wind, meridional wind, and temperature. So I'm looking at all kinds of different scores, and if they happen to be in that upper left triangle, it means that the multiphysics scheme is better than the control. And if they're on the diagonal, they're just as good. Then the model error representation didn't help. It didn't improve the forecast. And so up here, we see that in 66 cases, the physics was better than the control. Excuse me, in 138, the physics was better than the control, and out of those, 66 were statistically significant. The numbers don't matter, but what you can see overall is that there are improvements by the model error schemes. They tend to be clustering more in this upper left compared to control. The improvements are not great, but they are significant. And there are obviously also cases where they get worse. So for example, here, this means that by including a stochastic backscatter scheme, some of these forecasts got worse than those of the multiphysics. So in conclusion, both backscatter and multiphysics are better than the control. The stochastic backscatter is actually, in more often of the cases, it's better than the multiphysics, and their combination is best. and to just
You said it, to which variables does this refer? On which scale?
U, B, and T, good point. And so I also showed 2 different forecasting times there, which was 12 and 60 hours. So I'm trying to look at everything with those scatter plots, kind of. And this is just here a summary in terms of percentages. Okay, I'm almost done, but here's my challenge to the mathematicians among us, among you. So it will be very interesting to see why, or in which cases, the multiphysics is better than the backscatter scheme or vice versa, and learn from this. And I guess there was a subtlety that I didn't emphasize enough. It turns out that in the free atmosphere, so in the higher levels, the stochastic backscatter scheme tends to outperform the multiphysics ensemble. But in the down boundary layer near the surface, to which those mesoscale ensembles actually are aimed to predict, the multiphysics seems to be better than the backscatter scheme. And it would be really nice to understand exactly why this is, and then use this information and incorporate it in our stochastic parameterization schemes to have a representation of why the multiphysics near the surface is best. And this is a very complex problem, and I'm just trying to show this here. So for example, here's the spread of temperature for one particular forecast, and this is the error. So we would like that the spread matches the map of error perfectly if possible. And this is here for temperature on the right side, wind on the left, control multiphysics and backscatter. And so if you look at these things, we do see some patterns. So we see that here's some sort of front, which leads to a large error in the mean, in the forecast. And this is kind of in here, but it's not captured enough. The multiphysics clearly adds a bit to it. And then here's the backscatter, which adds a lot of this uncertainty. But maybe there are areas, for example, here where it's not doing it for the right reason. And so this is a high-dimensional problem. It's not obvious how to extract the information why a scheme is actually better, why an ensemble system is better than another one. I'm going to skip this. And so my challenge is, it would be very interesting to me to see how we can incorporate the unstructural uncertainty estimated, for example, by the multi-models into stochastic parameterizations. And I'm wondering if there could be simplified models that the mathematicians and the statisticians, maybe in a Bayesian approach, could actually look into this problem and could learn something from that we could then test in higher dimensional models. But to come to the conclusions, I hope I have shown that stochastic parameterizations have the potential to reduce model error by changing mean and variance. I hope I've demonstrated that a new stochastic kinetic energy backscatter scheme produces a more skillful ensemble and reduces certain aspects of systematic model error, and in general increases the predictability across a wide range of scales. I have also shown that the stochastic backscatter outperforms in general the multiphysics ensemble for this particular mesoscale ensemble system. This might not be generalizable to other ensemble systems. However, near the surface, the opposite is the truth, and I would really like to understand better why that is. And then incorporate that into the backscatter scheme. And finally, I tried to make the point that the stochastic backscatter schemes, albeit maybe their physical justification could be improved, especially in the context of model error growth and where you have to inject those the scales of uncertainty, that they provide a framework for a hierarchical parameterization strategy where the stochastic parameterization for the lower resolution is informed by higher resolution models. Future work, I'd like to understand model error better. I would like to inform more parameters of the scheme from coarse-grained high-resolution output, and I think there's a lot of work along these lines undergoing at ECMWF right now. Like to understand the impact on climate sensitivity. How do these model uncertainties impact our estimate of climate, or how would they change, or would they change our climate sensitivity estimates in long runs in the context of climate change, for example. And I'd like to understand better the consequences for error growth and predictability. Thanks very much.
Thank you very much, Judith. Are there some questions? Yes, Chris.
You used the word multi rather a lot of times, and I got a little bit confused. So could you just quickly say what the difference is or the sameness between multi-parameterization and multi-physics?
My apologies, it's the same thing.
Okay, thanks.
Sorry.
I'm a turbulence person, largely, and we've been doing a lot of work on the way in which sharp boundaries form in two-dimensional and three-dimensional turbulence. And it's, of course, got interest in engineering problems like wakes and so on. And if you use, as they do, an equivalent type of large eddy simulation, they resolve the larger scales, and the smaller scales they use a K epsilon model or whatever it is. Then they find that the edges of wakes and boundary layers or kind of blocked regions are too thick. So one of the approaches being considered is essentially a sort of upscale process. But the important point, and this is my question, is that the upscale assumption is that this upscale turbulence is very inhomogeneous. In other words, it will be very strong in relation to where you've got a boundary. So in other words, you first of all find where the sharp areas are, like sort of Glenn Schutz's sort of blocking fronts. And then you make your assumptions about the upscale process in relation to that moving front. So my question really is, first of all, number one, does stochastic backscatter, as it is used, sharpen fronts? I think the evidence I was seeing from your illustrations is yes, it does. And secondly, are you actually using that sharpening to actually selectively do your backscatter calculation in relation to this frontal region?
This is a very good question and very trying to give a succinct answer to this. So in the moment at ECMWF, the scheme injects energy where the dissipation is largest. So there is a sort of state dependence in there. I haven't said that, I'm sorry for the omission. I found that I do not necessarily have to do this. In the NWP context, we also looked at this at ECMWF. If you assume a constant dissipation rate everywhere, you don't do as well, but you still do pretty good. And I think in the NWP context, the idea is that we have regions where there's very strong error growth. So if you offer the model something there, your ensemble system will have spread. In regions that are pretty stable, you inject something, it damps out. So I'm not sure why exactly it is, but the fact is if we assume a constant dissipation rate everywhere, we're doing almost as good as making the system fully state dependent, which is the nicer thing to do. So I wonder if the characteristics of a flow where some perturbations grow and some do not is self-selective. I think this is why it's working without a state-dependent dissipation. To answer your question directly, if it sharpens the front, I am not sure if that happens on short time scales. And it would be interesting to look into. What was the second part of your question? Did this I wonder if...
You answered the point that you're using for dissipation, but the evidence now from the Japanese Earth simulator is very clear that, in fact, where you've got these sort of frontal structures which happen in turbulence, just where you get this maximum upscale transport is just outside those regions, not in those regions. And it is very, very inhomogeneous. So, I mean, clearly, in a way, that's one of the options you're considering, and I'm sure it's an area where these two areas of research, could be complementary.
And I think there's definitely other ways to implement those things. I think this is a great forum to think about other ways for developing modular parameterizations that might incorporate some of these aspects. And Glenn is thinking about a number of those too.
I mean, we're trying to cover a range of sorry. Well, I was going to say, sorry. I mean, we're trying to cover a range of processes here, which would potentially include what you've talked about, which might be to some extent covered by the fact that when the gradients are large, at least the diffusion acts strongly, and so that's a region of preferred dissipation. But also, we want to inject energy, for example, where tropical mesoscale convective systems are active. And that's a kind of different class, I think, of phenomenon to what you're talking about.
They have very intense edges, don't they, to those regions?
Yeah, but they're not characterized, I don't think they're characterized in the models by particularly strong gradients in the same way as, say, strong PV gradients would be in latitudes. So I think, it's trying to get a process, stochastic process, which will cover a range of different phenomena which are important in injecting energy back up the scale.
There's just one more point about this, is that one of the striking things that's emerged from this is that the traditional approach in turbulence is that we look at dissipation, where the dissipation is taking place. But actually, as we know in homogeneous turbulence, dissipation takes place because energy is being transported to that region. And if the flow is very inhomogeneous, as it is round fronts and so on, in fact, the critical region is not actually where the dissipation is taking place, but where the energy is being transported downwards. And those are two separate places in space. And it's where energy is being transported downwards across a gradient. That's where actually you get a lot of upscale transport. So there's dissipation flux and dissipation. And actually, I would have said it's the dissipation flux is the critical way of defining this. But maybe that's something in the future.
Richard, you had a hand up earlier.
Yeah, I was very interested in the sensitivity to the convectively coupled waves. Have you looked at that in any detail? I mean, it was a very big sensitivity of the spectrum that you were showing. So have you tried different parameter settings from the stochastic schemes and looked at the effect on the spectrum, or is that just a once-off result?
No, I have not done that, but I tried to understand why those connectively coupled waves are better or not, and I tried to trigger MJO and things like this. I showed this. The thing is, this is right. These plots were the signal compared to a background, and so they might overemphasize some aspects. If you look at the raw data, it might be a bit different. So yes, it would be very interesting to look at the details, no doubt, and also to look in other models. And those waves have been greatly improved by different connective parameterizations since then.
I think Frank had the next question.
It's the same question.
It's the same question, is that okay?
Jeff.
Judith, Martin this morning said that the backscatter scheme at ECMWF was not being applied in the planetary boundary layer. Are you applying the backscatter scheme in the boundary layer?
Is there
And if not, why would you expect good results in terms of dispersion in the boundary layer from the stochastic backscaters?
So the big difference is that I assume a constant dissipation rate right now. So yes, I do, but not for the right reason. And so for the atmospheric scientists, I don't think these backscatter schemes, maybe a bit at the Met Office, they have not been verified at the